Here's a strange fact about the model reading this sentence. If it happens to be a transformer, understand a sentence twice as long, and the effort roughly quadruples. Understand one 10 times as long, and the cost isn't 10 times greater. It's closer to 100 times greater. Attention, the mechanism that made modern language models possible, compares every word in a passage to every other word. That's what lets it capture relationships across an entire page. But it also means the cost of reading grows with the square of the length. Feed a transformer a 100,000-word novel, and somewhere in its memory sits a grid of comparisons, 100,000 cells wide and 100,000 cells tall. For years, that was simply accepted as the price of understanding. Then, in 2023, a small group of researchers asked a different question. What if a model didn't need to compare every word to every other word at all? What if, instead, it just carried a running memory forward? The way a person reading a novel doesn't reread every page to understand a new one, but carries the plot, the characters, and the tone forward, updating a compact picture as they go? That idea became Mamba. And to see why it works, we need to go back to a much older idea than the transformer. One borrowed from control engineering, not language. Long before anyone was modeling language, engineers were modeling systems that change over time. The temperature of a room, the position of a satellite, the voltage in a circuit. They describe these systems with what's called a state space model. At any moment, the system has a hidden internal state, a compressed summary of everything that's happened so far. A new input arrives, it updates that state according to a simple rule, and the state produces an output. No need to remember every past input individually. The state already contains everything relevant, compressed into a fixed-size sketch. In the 1960s, this framework helped land spacecraft. In 2020, a piece of math called HIP-PO showed something remarkable. You could design that compression so it preserved the entire history of a signal with mathematically optimal accuracy, weighting recent information more heavily without discarding the old. In other words, you could build a memory that never has to be reread, a running summary that stays useful no matter how long the sequence grows. That's the seed of Mamba's predecessor, a model called S4. Take that continuous state space idea, discretize it into steps a computer can process, and you get a sequence model that scales linearly, not quadratically. Double the input length, and the compute roughly doubles too, not quadruples. That alone made it attractive. But S4 had a serious limitation. Its internal update rule, the equations that decide how the state changes, was fixed once training finished. The same rule applied to every token, every time, regardless of what that token actually was. That's called time invariance, and it's a problem. Because language isn't invariant. Some words matter enormously, others are filler. A name introduced on page 1 might matter again, 300 pages later. A stray adjective almost never will. A model whose update rule can't tell the difference has no way to decide what to keep and what to let fade. It compresses everything with the same blind formula, whether the input is the answer to the question or noise around it. This is where Mamba's actual contribution comes in, and it's a small change with a large consequence. Mamba makes the update rule depend on the input itself. 3 parameters that govern how the state absorbs new information. How much of the new token to let in, how much of the old state to keep, and how the state gets read back out, are no longer fixed constants. They're computed fresh from the current token at every single step. In practice, this means the model can learn to open the gate wide for a token that matters and nearly close it for one that doesn't. It can learn to hold on to a fact from far earlier in a sequence precisely because the input told it to, and let go of something irrelevant a moment later. That's the selective and selective state space model, which is what the S in Mamba's underlying method actually stands for. It's the difference between a sponge that absorbs everything at a constant rate and a filter that decides, token by token, what's worth absorbing at all. But selectivity creates a new problem, and it's the reason nobody had shipped this idea successfully before. The old trick that made S4 fast, a mathematical shortcut called a convolution, which let the whole sequence be processed at once instead of one step at a time, only works when the update rule stays fixed. The moment the parameters change at every step, that shortcut disappears. You're back to a strictly sequential recurrence. Compute state 1, then state 2 from state 1, then state 3 from state 2, each one waiting on the last. On a GPU built to do thousands of things in parallel, a strictly sequential loop is close to the worst possible workload. This is the part where Mamba's authors stopped being mathematicians and became systems engineers. Their fix was a hardware-aware parallel scan. The recurrence itself can't be avoided, but the way it touches memory can be redesigned. Ordinarily, expanding the state for every token and every input channel would create an enormous intermediate tensor that has to be written out to the GPU's slow, high-bandwidth memory and read back in over and over. Mamba never materializes that expanded state in slow memory at all. It performs the expansion and the recurrence together, inside the GPU's small, extremely fast on-chip memory. Using a parallel scan algorithm that restructures the sequential dependency into a tree of operations that can still run largely in parallel. The result looks from the outside like a simple loop through the sequence. Underneath, it's a carefully engineered fusion of math and memory management that keeps the expensive intermediate values off the slow path entirely. That single engineering decision is most of the reason Mamba can be selective and still fast. The payoff shows up clearly at inference time. A transformer generating text has to keep a growing cache of every pass token's key and value vectors, the so-called KV cache, and that cache grows linearly with every new token, eventually dominating memory and slowing generation down. Mamba doesn't need one. Its entire history is already folded into a fixed-size state that gets updated, not appended to. Generating the next token costs the same whether you're at token 100 or token 100,000. In benchmarks that translated to several times higher throughput than comparably sized transformers at long sequence lengths, and the ability to handle context windows that would be prohibitively expensive otherwise. None of this makes Mamba a strict replacement for attention, and it's worth being honest about where it struggles. Tasks that require pulling one exact fact from far back in a long context, precise copying, exact retrieval, are exactly the kind of thing attention is naturally good at. Because attention can look directly at any past token, while a state space model has to have chosen at the time to keep that information compressed into its state. If it didn't, the information is simply gone. That's part of why some of the strongest systems built on this idea don't replace attention entirely. They interleave Mamba-style layers with a smaller number of attention layers, using cheap linear time layers for the bulk of the sequence, and reserving expensive quadratic attention for where exact recall really matters. What Mamba really represents isn't the end of attention. It's proof that the quadratic cost, long treated as an unavoidable tax on understanding language, was in fact a design choice. One specific way of solving the problem of long-range memory, not the only one. A 60-year-old idea from control theory, given the ability to decide for itself what to remember, turned out to be enough to compete with the mechanism that defined an entire generation of AI. The lesson underneath the equations is a simple one. Sometimes the fastest way forward isn't a bigger version of the thing you already have. It's an old idea, asked a new question. That's all for today in Dots and Arrows. See you in the next